Hello. Okay, so we have this statics problem here. Let me pull it up. Oh, oops. Okay, so we have this statics problem here. And it's basically just tell us the tension or compression in each of these joints based on this given force here. So this question is pretty easy once you know how to do it. It's just anything in 3D takes a while. So the best way to start off is that we have a really obvious place. Like if you look at the answers that they want, they start off with FAD, FBD, and FCD. We know that these are all the members connecting these. So what we're going to do is start writing out their components and all that. So how do we find their components? Well, we need to find the unit vector or the components of this vector, and then we can convert it into a unit vector. So I'll just write out quickly what each vector is, or sorry, the point. And I already I'm writing this down off of some separate notes. So, okay, so we know, remember, final minus initial. So we have our final point as D. D is final. And then we're going to have an initial point at all of these. So we're going to get a bunch of components. So we'll write them down as AD. Okay. So then we would get final minus initial. So 1 minus 0, 1, 2 minus 0, 2, 2. Okay, BD. Final minus initial, 6 minus 5. So final minus initial. I always get initial. Okay, so 1 minus 6, negative 5. Sorry. Negative 1.5. And 2. Final minus initial. And then we would do the same. Final minus initial. 1.5. 2. Okay, so now we need a unit vector. If we remember what a unit vector is, it is our vector. A vector we'll just call u over its magnitude of u. The magnitude is just like taking the square root of all the members squared. So we'll do that. So we get, this is 9. If you take 4 squared plus 4 squared plus 1 squared, so 9. So we're going to have 3, or divide by 3. 3, so we're going to get 1/3, 2/3, and 2/3. And so this is a little bit more complicated, but I believe it comes out to roughly 5.6. It's probably best to just put the exact square root, but that's what it is about. So you get negative 5 over 5.6, comma, negative 1.5 over 5.6, and 2 over 5. Sorry, ran out of room. 2 over 5.6. And then you would do the same. And the square root, or the unit vector, or the magnitude of the vector is 2.7 roughly. Negative 1.5, 2.7, comma 2 over 2.7. Okay, so this, sorry, they're all sideways. This is the unit vector, so this is the component. So if we plug in like a force into this, we know our components and how they'll all equal up. So what we can do is just plug into matrix calculator, system of equations, and yeah, this is the right one. So let me make this smaller so you can see my inputs. So we see we're going to align it with our x values. our y values, and our z values. So we know our x values are all 1/3 -5 over 0.6, and then 1/2. Or sorry, yeah. So we know all of our x components, and we put them all in a row of these. This is AD, BC, and CD. So just how you set up a normal matrix. Oops. So we're going to get all of them in a row. Same with our y's, z's. Or you could think of it as adding all of your your components of all of the same. So this is all AD right here, BC, and BD. Okay. So then, if you remember, this -200, 460. So that is up here. This is the known force. So we know -200I. This is the x, this whole row right here, x, -200. Our j is our y. So we just set these forces equal to each other, and we'll get an output. Oh, shit. Oh, something like this. So we know AD, the tension, and AD is equal to, sorry, I'll write it over here, is 394 BD. Oh, I wrote BC on my paper, whoops. BD is equal to 186, and CD is -444. And so now we have these units, but we also have this negative. So how do we know what's negative and what's positive? So you can kind of infer that we know that this is going to be going in the negative. This force was arbitrarily drawn in our drawing to be in this direction where it is. And so it's really in this negative x direction. So it's this way, and then it's in this positive direction. So we can think of it that way. Or sorry. It would be in this direction, negative x, positive y. Yeah. So what that means is that we're going to have a force that's leaning on these members here and then stretching out this member. So what this tells us is that these two are in compression, because we can just visually interpret that they're in compression, and this one is in tension. Okay. So now we have our AD, our BC, oops, wrong assignment, AD, BD, and CD. So now we need to find our forces for, sorry, delete all of this. We need our forces for BC, AC, and EC. And I'm going to zoom back in. So we have to find a link or a point that we can calculate them all easily. So we know this point right here. Look at it. We have CE, BC, and AC. All of them at one point. So we're going to use point C. So now we know we have B, E, A. Okay. So now we know that there's going to be the only force acting on this, because it's due to it being in static equilibrium, is this force up here, up top. And we've solved for all these components right here. All these components we know. And we know that the only component on here is C. That's the only component. So we can write back in what CD's components were. So we can just say that we know CD was equal to um, uh, uh, our unit vector for CD, since we know a force, the compression force that it's in, 144 or 444. So we know it's going to be 1 over 2.7, comma, negative 1.5 over 2.7, comma, 2 over 2.7. Okay, and I'm running out of room again because I am writing massive. Okay, so now we know, okay, and then I forgot the times left 144. So we can quickly throw this in our calculator to find our components. So I'll put this in Desmos. Oh well, actually, I'll just pull up the calculator here. So we know 1 divided by 2.7 times 444, negative. So we get negative 164, the x direction. Okay. So now negative 1.5 divided by 2.7 times 444 negative, we get negative 246.7. I keep on losing my mouse. Okay. And then 2 divided by 2.7 times 444 negative gets us negative 328. What was the last point? 0.9. I'll just round it. Okay. So now what does this mean? So we know that this is the only forces acting on C, the only tension force we have on C. So if we go back to our page, since we know these are the only forces, and we know this is in static equilibrium, we can then set them all equal to them. And I guess I did my math wrong on some part of these. I got my tension and compression mixed up, but I got all the right values. So you get 165, 247, and 330, which is basically 328. And I also did a lot of rounding, so that's to be expected that I would get some error in that. But I get about the right answer. So that is about it. Oh, okay, here.